start recording. Just go over this. This is review, and it's a really short worksheet just because you guys just had an exam, and I didn't want to keep you guys here for a super long time. So I did make these with the intent of preparing you for Thursday's lecture. So it seems easy. Well, if it seems easy, that's good. But when we're looking for resonance forms, you're just like, again, looking for that general. Okay. This general format where like X is right next to a double bond and X has like a lone pair, which is basically just a negative charge usually. Well, not always, but a lone pair or a negative charge or positive charge or a radical. So we have a positive charge right next to a double bond. And if it's a positive charge next to the double bonds, then the double bond goes towards the positive charge. If that was a negative charge, it would go towards the double bond, but that's not what we're doing here. So then we have the double bond here and the positive charge over here on the Z atom. So like if there's a charge, it usually moves to where the Z atom was. So if it was a negative charge, then this would be negative, but it's positive. And it's the electrons moving, not the positive charge, but you can see that the positive charge moved. So same thing with the second one. And if you have any questions, feel free to stop me if this is review, so hopefully it's clear. So same format, we can do this. Put the positive charge there. Can I form any other resonance forms or draw? No, yeah, because if you look at it like this, then that's the X atom here, and that's not the, like it's not close enough to the double bonds. The positive charge isn't close enough, so we can't draw a resonance form. So this is the only resonance form there. Oh, 1, 3, 2, 4 down. Okay. Oh, shoot. Okay. So for this one, again, we have this form here. So we can do the double bond just like on the last one. And we get this. Can we draw any other resonance forms with this? Yeah, we can. So I'll redraw it to make it not as cluttered. But also here, if we look at this form, we can see that the positive charge is close enough to the double bond. It's right next to it. So we can go this way. So now this double bond is in the same spot. This moved, and we have the positive charge here. So we have two resonance forms for this. Okay. Hopefully that makes sense. And I also asked you to draw the mechanism for the HCl reaction with the double bond, which will be relevant on Thursday in your final, so it's good to know. Can anybody describe the first step of this to me? Okay, it might be hard to put into words. Describing the mechanism for number 2. That's the question. What's our nucleophile? Okay, we've been looking at SN1 and SN2 reactions a lot, but chlorine, yeah, for the first step, yeah, this is alkene reactions. Yes, that's the product of the reaction, but I'm asking for the mechanism to show like how we get to that specific product. So what's the first step of this mechanism is what I was trying to get at. What is acting as nucleophile for a first step? The alkene, yeah, the alkene has a lot of electron density, so it's going to act as a nucleophile. And do that. There's a dipole in hydrochloric acid because chlorine is pretty electronegative, so the hydrogen on it can act as an electrophile to react with the nucleophile. So this is the first step. The alkene attacks the hydrogen and kicks out the chlorine there. Then we get an intermediate. So the hydrogen attaches here. It could theoretically attach at either of the carbons of the double bond, but it attaches here so that we get this positive charge. And we get this positive charge because of what drives it to be here. If we had this positive charge, what would the stability be compared to that one? Secondary versus tertiary positions, which one is more stable? Tertiary, yes, thank you. So because of that, that's why the hydrogen goes on a secondary position and the cation forms on the tertiary position because that's the more stable one. And now we have well, if we put the positive charge on the secondary position, then we could do a hydride shift, yes, but that, I mean, I don't think it would be wrong to do that, but you're just adding extra steps to your mechanism, so it's kind of simpler to just say that the positive charge starts here if you have an option between a secondary and a tertiary position. But if we had like something like this, maybe it would do, actually no, it probably wouldn't do a full shift because it usually only shifts cations if you have, I'll just go off topic, I guess, and draw over here. Like if you had this cation, this is secondary, but if we do a hydride shift, then the hydrogen's here. It went from secondary to tertiary. So because of that, it formed a more stable cation. So it doesn't usually wants to go like from secondary to secondary to tertiary. And like if your mechanism involved putting the cation down here, then yes, that would have been fine. But I'm just explaining like you can't always have a hydride shift just whenever you want. Okay. So this is the cation and it's electron deficient. So what does that make it react as? A nucleophile or an electrophile? Cation here. A nucleophile usually has electrons to donate, so this is electron deficient. It's going to act as an electrophile. It's going to react with the chlorine that we kicked out earlier. It's going to act as a nucleophile and just attack the positive charge. So we get that product by this mechanism. And this is relevant because, well, if you haven't read the book, you might not know yet, but next lecture, I don't know where to put this. I guess I can scroll down. Okay, so like you can see that a cation forms as an intermediate for this reaction of an alkene with HCl. If we reacted HCl with this, then like an intermediate could be this cation forming. And just like we talked about in the first question, when there's a cation right next to a double bond, there can be resonance. So this intermediate that forms has a resonance form. And then the cation goes over here. And then the chlorine can attack that. So you've shifted the position that gets attacked by the chlorine when you have these two double bonds right next to each other and you react it with HCl. And I know I'm getting like into your next lecture, but I mean, I connected it with these first two questions. So hopefully this seems pretty clear right now. And like this is, I have to put something else like, no, that is a different product, I think. Maybe I should put the methyl group somewhere else, but like the point is the cation moved and then the chlorine attacks a different position than you'd initially expect. So that's what you're going to be getting into a bit on Thursday. If you have any questions about that, you can ask, but hopefully that makes sense. Okay, for number 3, the more heat something has, which means it has a higher temperature, does that mean it has less energy? Is that true or false? Is the question not clear, or are people just scared to answer? Does it need explanation? You think false? You're correct. It is false. I'm not trying to make a trick question. Just heat is a form of energy. So the more heat a system has, the more energy it has because heat is energy. And this is relevant to your next lecture as well, but I don't think I should get into that. I'll let you guys see it there first. But the temperature that a reaction occurs at, specifically this reaction with the two double bonds next to each other, is kind of important. That's why I brought it up, to kind of get that idea into your head. Temperature increasing means higher energy. Okay. Hopefully some of you looked at this before your exam, but if you didn't, that's fine. Just, it was here. Does anybody have an idea on how to start these? You do? Okay. So it's usually easier to start from the end and work towards the beginning. So I guess we can look at it that way. So you should recognize, yeah, copper, like the copper complex reaction, because like we're forming new carbon-carbon bonds, and you only know like 2 reactions that can do that, and the other reaction only works with primary positions, which this is tertiary. So you're right, copper complex, and you're right, propyl group, because we added 3 carbons here. So can draw it like that. And then I'm pretty sure it requires an ether solvent, so you should put THF. And what is that reacting with? What do these Gilman reagents react with usually? An alkyl halide, yes. It doesn't matter what you use, so yeah, that works. It could be bromine or chlorine, maybe iodine, but that's usually difficult to get. Okay, so how do we get to this bromine here? What would be a precursor to the bromine being in that position? Well, yes, that would be the reaction. And what is it reacting with? Two methyl pentane. Well, this is 2-methylpentane, but what's missing here? If we just did HBr with an alkane, nothing would happen. Um, I'm not sure what you're getting at. Are you thinking like an SN1 reaction with this bromine we started with to move? Okay. I could see that maybe, but like counting on a hydride shift, that's what it sounds like you're thinking. Um, yeah, I'm not sure about that. That's usually not what you would do in a synthetic procedure. You wouldn't do a reaction like an SN1 to hope that it does a alkyl or a hydride shift to move like the bromine here. So um, I'll go ahead and say like you had the right reaction going backwards, and like let's just say we had an alcohol here. We did an SN1 substitution to replace the alcohol with a bromine. Okay, so how could we have gotten an alcohol on this position? What kind of reaction could we do? You only know like two reactions, or I have two reactions to add one singular alcohol to something. This is kind of old, but you'll have to know it next week or whenever your final is. Okay, so to something we're reacting with is going to be a double bond, but we want the alcohol to be on this specific position. So what reaction do we have to use? Mercury is involved, yes. Yeah, that's it. It's mercury acetate. It's getting a bit crowded. And there's two steps. What's the second step? These are both very important. Yep. NaBH4. You have to put the 1 and the 2. Considering online formats, I'm not sure if you get a chance to miss that, but they're both very important. And then how do we get from the alkyl halide to this double bond? Yeah, KOH works. Actually, It does work, but like, okay, so it usually wants to use like these specific conditions, which does involve KOH, but it's like the base with a polar protic solvent. That's what's important. You have to have both because like if you had KOH and acetonitrile as your solvent, then it might do an SN2 mechanism to replace the bromine with a hydroxide. So that's why both of these are important. And you should understand why the solvent is important now. Like you shouldn't just put KOH by itself because of the competing SN2 reaction. So we take the alkyl halide and we form a double bond, and the double bond is the side-step product that doesn't go the other way because that wouldn't be as stable. And then we do the oxymercuration reaction to put the alcohol on the Markovnikov spot. And then we do SN1 substitution to get a bromine there, and then we add the propyl group. So this is a kind of tough synthesis problem, but if it's tougher than what you see on your exams, then this is good practice. So unless there are any questions, exam was nowhere. Okay, yeah, that's good to hear. Even if you can't get these, it's good practice to think about. Okay, so how about this one? Does anybody have an idea of how to start it or work backwards or anything? Yeah, that's correct. So the NBS H nu reaction, I'll just put it over here. Oh, okay. It does allylic bromination. So like it could add the not exactly like that. Why did I do that? Could add the bromine like here, right next to the double bond, because it's a radical mechanism and it will form the most stable radical and then add the bromine there. And here, like, we only have one position that's not in a double bond. It's right here. And that's not allylic, but it's benzylic, so it's even better than allylic. So if we do NBS with H nu, then it's going to add the bromine on that one primary position there. So this would be the product. And then what could we do from here? Again, we're adding carbon, so we have two potential reactions we could use. We could use this, or we could use this. Those are basically the only two options we have. So we have a primary alkyl halide here. And you should remember that this is an SN2 reaction when it does reactions, and it only works with primary positions, which we have here. So we could theoretically use the acetylide anion. Could technically also use the copper complex, but doesn't seem like anybody has an idea, but I don't think we can make the reaction work with the Gilman reagent. That's not how I envisioned it. If anybody tried to do it that way, you can describe it, but I'll go with the acetylide otherwise. Doesn't look like anybody does. So we're adding 2 carbons. So the acetylide we're going to be using is just, we have a counter ion for the negative charge, and it's just 2 carbons. That reaction in THF. And then we get this product of the triple bond here. And how can we get from the triple bond to that product? This is another reaction you guys need to know. Going from an alkyne, a terminal alkyne, to an aldehyde. It might look like cleavage, but count your carbons. We have 1, 2, 3 carbons here, and then 1, 2, 3 carbons here. We're not cleaving anything. It's the same number of carbons. If it was cleavage, which it could have been, then like I probably would have done this. Yeah, that's the right reagents. But just like for reference, if it was cleavage, well, first we would have had to reduce it to a double bond if we wanted to get an aldehyde, because whenever you cleave a triple bond, you get a carboxylic acid. It doesn't matter what you use. But if we were to cleave this as a double bond, we'd probably get like this as a product, 2 carbons, and we'd get the byproduct of just 1 carbon like this. So just so you know, like that is really easy to make a mistake with, and that was part of what I was going for, trying to make this more difficult because it kind of looks like cleavage, but if you count your carbons, you can see that we didn't get rid of any. So like Jared pointed out, we're going to use the BH3 reaction, and it's 2 steps. What's the second step? Yeah, hydrogen peroxide and hydroxide. Yep. I'm just gonna erase these because I'm planning on uploading this as an answer key. So yeah, hydrogen peroxide and base. And that leads to the, just like if we were reacting with a double bond, it leads to, it leads to the Antimer-Kovnikov product. So like if it was reacting with a double bond here, we'd get an alcohol on that primary position, but because it's a triple bond, it leads to an aldehyde. So that's just like, again, review the mercury reactions leads to Markovnikov oxidation, and then the borane leads to anti-Markovnikov. Like I said, I made this really short because I didn't want to really waste you guys' time after an exam. I could keep talking and get into your next lecture if you wanted, but I'm assuming people don't want to stay forever. So if you guys just want me to end it here, I'm fine with that. I don't have any ideas off the top of my head for more review, besides just more resonance or more synthesis. Okay. That sounds good then. Happy studying. Thanks. Yeah, thank you guys for coming. Guess I'll end the recording.